Hello, my name is John Cody. I'm an engineer from Vancouver, Canada. Today I'd like to talk to you about a discovery I made in Universal Hyperbolic Geometry. Today I'll be talking about my discovery of a general formula for the Quadria of the Projective Quadrangle. Here we have an image of the projective plane in Universal Hyperbolic Geometry. Zoom in on it. It consists of the null circle in blue, and here we have a quadrangle consisting of projective points A1, A2, A3, and A4. And we also have quadrants Q1 between projective points A1 and A2, quadrants Q2 between projective points A2 and A3, quadrants Q3 between A3 and A4, and quadrants Q4 between A4 and A1. And we also have spreads S1 at point 1, which is the spread between lines between A4 and A1 and before line A1, A2. So that's the spread S1. And similarly, we have spread S2 between lines A1 and A2 and A2 and A3. Spread S3 between line A2, A3 and line A3, A4, and spread between line A3, A4 and line A4, A1. And the quantity that I'll be talking about is this quantity A, which I'm calling the Quadria of the Projective Quadrangle. Now the main result is that the Quadria of the projective quadrangle is given by this quadratic equation. In fact, there's a pair of quadratic equations that are compatible. And this pair of quadratic equations, compatible equations, has a common solution given right here. So the equation is A is for the Quadria here. This quadratic equation number 1 is A minus Q1, Q2, S2 minus Q3, Q4, S4 equals 4 times Q1 times Q2 times Q3 times Q4 times 1 minus S1 times 1 minus S3. That's the first quadratic equation. And the second quadratic equation is A minus Q1, Q4, S1 minus Q2, Q3, S3, all that squared equals 4 times Q1, Q2, Q3, Q4 times 1 minus S2 times 1 minus S4. And there's a theorem in a book by Norman Wildberger called Divine Proportions. And theorem number 1 in that book states that if you have two compatible quadratic equations, then they have a common solution, and the common solution is given by a formula which results in this formula here. Okay, so the two equations represent two different triangulations of the quadrangle. So here I have the first figure 1, I have the quadrangle A1, A2, A3, A4, and there's a chord between A1 and A3. So this divides the quadrangle into two triangles with quadrias A2 and A4. And similarly, we have the same quadrangle in figure 2, and we've triangulated it with a chord between A2 and A4. These quantities A1 and A3 are the quadrias in Universal Hyperbolic Geometry. So A1 is going to be Q1 times Q4, Q1 times Q4 times S1. A2 is Q1 times Q2 times S2. So that's A2 is here, so it's Q1 times Q2 times S2, the spread here. And similarly with A3, it's Q2 times Q3 times S3. And A4 over here is quadrangle is Q3 times Q4 times S4. And when we replace these quantities with the A2 and A4, the two equations become the Quadria A of the quadrangle is equal to A2, or Quadria of the quadrangle minus A2 minus A4 squared equals 4 times Q1, Q2, Q3, Q4, 1 minus S1, 1 minus S3. So that corresponds to this figure here. So we have A2 and A4 appearing on the left-hand side. And you notice on the right-hand side, the S1 and S3 are the spreads where the chord divides the quadrangle into two triangles. And in figure 2, we have this equation is the quadria A minus the quadria of the triangle A1 minus the quadria of the triangle A3. All that squared equals 4 times Q1, Q2, Q3, Q4 times 1 minus S2 and times 1 minus S4. And in this case, the chord divides the quadrangle at node S2 and S4 at projective point A2 and A4. And the unique solution from the quadratic compatibility theorem turns out to be A is the quadria, the quantity we're interested in, is this equal to A2 plus A4 plus A1 plus A3 all over 2 minus 4 times Q1, Q2, Q3, Q4 times 1 minus S1 times 1 minus S3 minus 1 minus S2 times 1 minus S4 all over 2 times A2 plus A4 minus A1 times A3, or minus A3. Okay, so that's the main result, and I'll just go through what all this means, review of universal hyperbolic geometry. So in universal hyperbolic geometry, a hyperbolic point is a 3 proportion A of x to y to z enclosed in square brackets. A hyperbolic line is a 3 proportion L, it's defined as L1 to M1 to N1, L to M to N, enclosed in round brackets. We have round brackets here. The point A, x to y to z, is dual to the line L, L to M to N, precisely when x to y to z equals L to M to N. The point A lies on the line L, or equivalently, L passes through A precisely when L times x plus M times y minus N times z is equal to 0. And for more definitions from the basics of universal hyperbolic geometry, we have the quadrants between points A1, which is the proportion x1 to y1 to z1, and A2, x2 to y2 to z2 is the number q of A1, A2 is defined as 1 minus x1 times x2 plus y1 times y2 minus z1 times z2 all squared divided by x1 squared plus y1 squared minus z1 squared times x2 squared plus y2 squared minus z2 squared. That's the quadrants. The spread between lines L1 and L2, L1 is L1, M1 to N1, L2 is L2 to M2 to N2, is the number S for spread between lines L1 and L2, and that's defined as 1 minus L1 times L2 plus M1 times M2 minus N1 times N2, all that squared, all divided by L1 squared plus M1 squared minus N1 squared times L2 squared plus M2 squared minus N2 squared, all that squared. Furthermore, we have some for more definition, the join of points. If A1, which is defined as x1 to y1 to z1, and A2, x2 to y2 to z2 are distinct points, then there is exactly one line which passes through them both, namely L, the line L, which is A1 to A1, A2, is defined as y1 z2 minus y2 z1 is the proportion to z1 x2 minus z2 x1 to x2 y1 minus x1 y2. Furthermore, the meet of lines, if L1 is L1 to M1 to N1, and line 2, L2 is L2 to M2 to N2 are distinct lines, then there is exactly one point in which lies them both, namely the point A is L1, L2 is the meet of L1 and L2, and that's defined in square brackets M1 N2 minus M2 N1, N1 L2 minus N2 L1, L2 M1 minus L1 M2. Some more definitions. A triangle A1, A2, A3 is a set A1, A2, A3 of three distinct non-collinear points. And a trilateral is L1, L2, L3 is a set L1, L2, L3 of three distinct non-concurrent lines. There's a quadrangle, A1, A2, A3, A4 is a set A1, A2, A3, A4 of four distinct points. And a quadrilateral, L1, L2, L3, L4 is a set L1, L2, L3, L4 of four distinct non-concurrent lines. We say the quadria A of a triangle A1, A2, A3 with quadrances Q2, which is defined as Q of A1, A3, Q3 is quadrants Q1 or Q of A1, A2, and spread S1, which is the spread between A1, A2 and A1, A3, and that quadria is the number A, Q2, Q3, S1. Dually, the quadrille L of a trilateral L1, L2, L3 with spreads S2 is defined as the spread between L1 and L3, S3 defined as the spread between L1 and L2, and the quadrants Q1, which is defined as Q of L1, L2, L1, L3, the meet of L1, L2, and L1, L3 is the number L. This quadrille is S2 times S3 times Q1. The proof of the quadria of the projective quadrangle makes use of the quadratic compatibility theorem. And this is theorem 1 in the book Divine Proportions by Weilberger, which states that two quadratic equations, x minus p1 all squared equals r1 and x minus p2 all squared equals r2. These two compatible equations these two quadratic equations are compatible precisely when p1 minus p2 squared minus r1 plus r2, all of that squared, is equal to 4 times r1 times r2. In this case, if p1 is not equal to p2, then there is a unique common solution given by x is equal to p1 plus p2 over 2 minus r1 minus r2 divided all over 2 times p1 minus p2. And here I'll give the definition of the quadria of a projective quadrangle. The quadria A of a projective quadrangle A1, A2, A3, A4 is the common solution of two quadratic equations in A and the quadrants and spreads of the quadrangle. And here I'll state the quadria of the projective quadrangle theorem. Suppose A1, A2, A3, and A4 are distinct projective points with quadrants Q1 equal to Q of A1 and A2, Q2 the quadrants between A2 and A3, Q3 the quadrants between A3 and A4, Q4 the quadrants between A4 and A1, and spreads S1, which which is the spread between A1, A4 and A1, A2, S2, which is the spread between A1, A2 and A2, A3, S3, which is the spread between A2, A3 and A3, A4, and S4, the spread between A3, A4 and A4, A1, and Quadria A. Then the quadria of the projective quadrangle is the common solution of the following pair of quadratic equations. Quadria A is A minus Q1, Q2 times S2 minus Q3, Q4 times S4. All that squared is equal to 4 times Q1 times Q2 times Q3 times Q4 times 1 minus S1 times 1 minus S3. And the second quadratic equation is in A is A minus Q1 Q4 S1 minus Q2 times Q3 times S3. All of that squared is equal to 4 times Q1 Q2 Q3 Q4 times 1 minus S2 times 1 minus S4. That's the second equation. And the proof, by the quadratic compatibility theorem, these two quadratic equations are compatible, meaning that they satisfy this equation here, where P1 and R1 correspond to, the P1 is Q1, Q2, S2 plus Q2, Q3, Q4, S4, and the R1 is the right-hand side here, and P2 would be Q1, Q4, S1 plus Q2, Q3, S3, and R2 is this quantity here. If we substitute those into the condition of the quadratic compatibility theorem, into this equation, we get that they are precisely equal. Furthermore, when Q1, Q2, S2 plus Q3, Q4, S4 is not equal to Q1, Q4, S1 plus Q2, Q3, S3, then they have a unique common solution, which is the quadria A is then given by this expression here. The quadria A of the projective quadrangle is Q1, Q2, S2 plus Q2, Q3, Q4, S4 plus Q1, Q4, S1 plus Q2, Q3, S3 all over 2 minus 4 times Q1, Q2, Q3, Q4, 1 minus S1, 1 minus S3, minus 1 minus S2, 1 times 1 minus S4, all over 2 times Q1, Q2, S2 plus Q3, Q4, S4 minus Q1, Q4, S1 minus Q2, Q3, S3. And if these two quantities are equal, then the two quadratic equations are equivalent. It's the same equation, and there's up to 2 solutions in that case. Okay, so that was my discovery of the quadria of the projective quadrangle in universal hyperbolic geometry. Thank you.